All right, I think we have a quorum and it's 10 o'clock. So welcome back everyone to the second day of our CTech and MCNet summer school. And we are continuing with the lectures that you've already seen yesterday on the basics of Monte Carlo event generators and in the afternoon basics of QCD. So I'll just hand over to Stefan for the second part of, or third and fourth parts of his lecture.
All right, thanks, Frank. Welcome back, everyone, to this morning session. And let's dive right in. So just as a quick note, yesterday in the recitation sessions, I saw a lot of discussion about the small exercises that I put on my slides. And since I didn't put exercises on the slides for part 3 and 4, I thought, well, maybe it's time to challenge you a bit. And I've put exercises, one exercise on uploaded on the Indica page. So that one is a bit of a tough one. So someone has music in the background, not too bad. That one is not an immediately easy one, but I hope still it's going to be fun to discuss because it's not only applicable to the immediate problem at hand that is posed, but also to a wider array of problems. So we'll see. Don't feel discouraged if it doesn't work out. Anyway, so yesterday we had 2 hours of lectures that were an introduction to kind of the generic picture of how we think of simulating events in particle physics experiments, and went through a couple of numerical algorithms in order to facilitate that that simulation, meaning something like inversion sampling, rejection sampling, and sort of rejection sampling mixed with inversion sampling, that's then importance sampling. And then in the second lecture, we went through the generation of phase space and of matrix element for the highest energy scattering, the hard scattering, that typically lies that is at the core of, is the initial seed of the whole evolution of the event, and typically is then also the first thing to calculate when you perform an event generation. Today, we'll move on to sort of filling in more and more details into the events. And the first lecture today will be about, again, another numerical method, the Sudakov-Vitu algorithm, and why this is useful for generation of multi-parton states. Then Patenschauers and a very basic idea of how to combine those with the cross-section calculations for the hard scattering that we saw yesterday. And then, because I think it fits very nicely, multi-parton interactions. So it might well happen that we'll postpone the last point to after the coffee break. So I don't think that's a big issue. It fits nicely into this lecture, so that's why it's here, but very likely we'll probably postpone it. Okay, move on to the start of the lecture. So first, let me remind you of the Kinoshitali-Nauenberg theorem again, which says in popularized speak that infrared singularities, low energy or sort of low angle singularities in real emission diagrams cancel against alike singularities in virtual corrections. So we can take a radical and sort of really sort of almost religious approach to that, and say for the most enhanced parts of cross-section calculations beyond the lowest order, we'll actually say that the virtual corrections themselves are defined as negative the integral over the real corrections. And we can even say that if there are some cuts or sort of some constraints on the real emission kinematics. saying it another way is that the rate of the particles remaining the same in a certain state is negative the rate of the particles increasing at any scale t, even if that scale t is constrained by some kind of, say, for example, cuts, that you don't let things get too close in angle to each other. That's a radical kind of reinterpretation of the KLN theorem, that if you would be completely sort of blind to any of the real corrections, and any of the virtual corrections would actually be true. It's also the building block, the very first building block of what is called a parton shower. These parton showers will use exactly that relation in order to approximate virtual corrections by approximated real corrections, which only contain the singularities. And since these approximations are easy enough, they're actually iterable. So you can dress up partons with more and also particles with more and more radiation in a nice way, and at the same time make sure that everything is finite by including virtual corrections in this approximate way as well. So what is a parton shower? Best to think of the behavior of partons as being very similar to that of the decay of a radioactive isotope, in the sense that a radioactive isotope, or sort of the population of radioactive isotopes in your sample, let's say that is n, can only change to n+1 or n-1 due to splitting or decay at a particular time t, if it had not already changed at an earlier time t prime. Time in a particle physics simulation typically means we associate with scale, or something like the off-shellness of propagators. The higher off-shell propagators are, the shorter the time period. For shorter time period, these propagators can actually sort of exist, in a sense, due to the uncertainty principle. So think of time from now on as an energy scale, that the higher the energy scale, the shorter the time at which this thing can live. Now, the probability for not changing, say, sort of population of radioactive elements in a finite scale interval delta t is then 1 minus the interval times the probability for naive probability for this decay to occur. In the picture of partons that can radiate other partons because of these infrared singularities, this P is actually the splitting kernel that contains all the enhanced parts of the real correction, so all the virtuality. And this statement is simply a statement of total probability conservation, that the rate of no change is the rate of all possible changes, or the rate of no change and the rate of all possible changes add to unity. This is just what this says. Now, you can further subdivide this interval into very small integrals, intervals delta t over n. Then the probability for not changing in any of these small integrals is 1 minus this smaller sort of interval times the splitting kernel raised to the power of n. And if n approaches infinity, so you have infinitely small intervals, this will produce an exponential suppression that within the time from 0, or scale from 0 to delta t, not having an emission is or not having a decay is exponentially suppressed. This exponential suppression for no splitting is, in the speak of high energy physics, called a Sudakov form factor. Now, since no splitting means that the number of particles stays fixed, these Sudakov form factors actually introduce a way of introducing virtual corrections. Now, imagine you'd expand those out. So it's as a 1 minus this integral plus a half this integral squared, and so on and so on. The first term of that would be an approximation of a one-loop virtual correction. The second, so the integral squared, would be approximation of the two-loop correction, and so on and so on. So these pseudocofactors introduce what's called virtual corrections in a nice way by basically only relying on your approximate real corrections, which only contain the most infrared singular parts of the real emission diagrams, which we've already learned in the last lecture are universal, so independent of the actual hardest scattering that occurs in the process. So that's good, because that basically means that eventually you can use this in order to build a numerical algorithm in order to produce more than just a single emission. Before doing that, coming back to what is then the actual probability of a decay or a splitting of a particle at the scale t. That is the naive probability of the particle splitting, p of t, at a fixed time, times the probability of not having split in any small interval before the scale t, which is given by this exponential pseudocofactor here. In the following, I'll write these exponentials mostly as delta of t. If delta of t contains is written in terms of two arguments, what this means is typically that there are both upper and lower bounds specified. Here I've just not specified the lower bound because I was lazy. So how do we then move about and generate this? First, in order to it's good to to note here that this actually, as any decay process would, actually retains some memory. That a next decay at scale t only happens if it had not happened before at a higher scale. So the way how we derive this exponential factor also then means that the conservation of total probability, meaning that overall the rate for not emitting is 1 minus the rate of emitting once plus half the rate of emitting twice, so the integral squared and so on, actually develops a memory. So conservation of probability means that these decay processes, in a sense, have a memory. This is not something that we could use our previous algorithms for, because they'd always kind of reject, they'd always reject proposals and then start fresh without knowing anything about the rejection that you've just done. So we'll see in the following how to fix that with a thing called veto algorithm. Also, just as a kind of outlook to some of the more dedicated lectures on pattern showers that I think will come tomorrow, it's useful to look at this equation that defines the total probability, the decay probability at a fixed scale t, and see that we can actually rewrite this as a differential equation, that the derivative of the pseudocofactor delta is actually just the probability, so whatever you have in the exponent here, times delta, meaning that d log delta of is actually just the naive splitting probability. Why is that useful? It's useful because this is the way how we typically write down the evolution equations for, say, pattern distribution functions or fragmentation functions in quantum chromodynamics. The DGLAP equation can be written in this form. So that means that if we solve this differential equation with an appropriate definition of what these splitting functions p are, or what the right-hand side here is, we effectively solve the DGLAP equation. So we effectively produce some type of QCD effect that is present in nature. It's not just the analogy to radioactive decay that makes us believe that we want to solve this equation. So you'll hear lots more about this in the partner shower lecture. But for now, let me just think of how we can actually use this equation to correctly distribute samples of splitting times or splitting scales with this equation. And it's easy to see that right, if you want to solve this equation, then the cumulative function that you're actually looking after, if you want to use inversion sampling, is in fact just the pseudo factor itself. So if you integrate this out in order to get the cumulative, if you integrate over this in order to get the cumulative function, then you will just arrive yet again at a pseudo factor, which is something like the exponential of the primitive function or the integral of these splitting kernels. So simply using inversion sampling, we can actually distribute splitting scales, so scales where one parton splits into two partons, by simply saying that a random number equals this pseudo factor, and solve this for the time or the splitting scale t. With that, we've produced a sample of decay scales where one particle splits into two, or one parton splits into two. For example, a quark splits into a quark and a gluon, or a gluon splits into two gluons, or a gluon splits into two quarks, and so on. This really is the basic algorithm of a parton shower, because now once you split a particle, the decay product of that particle can split again and again and again, thus producing kind of a decay shower that forms the structure of a jet of partons. So in this way, parton showers can solve evolution equations, because evolution equations of this form, by simply sampling the splitting scales where kind of changes in the early evolution occur according to inversion sampling. Well, that would be nice, because that would be extremely efficient and fast. However, this is not quite what happens in real life, because the functions that we have to actually invert are typically too complicated to invert analytically. So the way how to go around that is to again invoke rejection sampling, just like we did in the first lecture when we saw that something was difficult to integrate. So what we did is we decided on a simple overestimate function that overestimates the probability distribution, and then use that in order to draw variables, to draw the interesting random variables from it, and then reject the random variable that we've drawn based on the comparison of another random variable with the ratio of the true distribution divided by the overestimate. Now, in the first lecture, what we then did is, well, once we rejected, we would simply restart the algorithm again, forgetting anything about the rejection or where the rejection had occurred. In this case, in the case of a process with memory, this can't work, because basically then you simply forget that you've already probed a particular scale and decided, well, there's not going to be a rejection there, and not going to be a rejection there. That would erase the memory. The correct thing to do is actually, in this case, in order to retain the memory, is to say, if you have rejected a branching to occur at scale t, then the next attempt of drawing another splitting scale t, it would start from the previous value. So meaning that you checked, maybe you start from a high value t0, or sort of low value t0. Then you check, did you decay at time t, t1? No. Then you check, well, did you decay at time t2 that is larger than t1? No. Maybe decay at t3 larger than t2. And then maybe eventually at t4 you actually decay. So in order to retain the memory, you have to do something, or to use this additional restart criterion that depends on your previous rejections. This is called the Sudakov-Mitu algorithm. Again, you'll hear more about it in the shower lecture. The important thing for here is now that in this way, Parton shells can actually solve complicated or sort of realistic evolution equations with realistic distributions from which to draw the splitting scales. For example, the D-Gleb splitting kernels, which have no inverse of their primitive function. I should note that typically the algorithm is actually run in exactly the opposite way. So you start from a very high scale and move down towards low scales. But it's slightly more difficult to prove this way. So if you want to prove the algorithm in this way, it makes it a bit more transparent. But technical details, I'd say. Now, of course, in nature, when you have partons that can branch into each other, there are many different competing decays that can occur. So, for example, a gluon can decay into two gluons, or it can decay into a quark-antiquark pair. Similarly, a quark can radiate gluons, or if you think about the standard model more broadly, it can also radiate photons. So the decays that you want to, that actually occurs at a particular scale t, is a combination of all of these channels. And we've already learned in the last lecture that the way how you handle competition between channels is relatively straightforward. I mean, you use the discrete transformation method. So what you could do is you could use the Sudakov-Mitu algorithm with a more complicated function that you that you use as your function from which you want to draw decay scales. That, for example, includes F1 and F2 for two different types of splittings. You produce a decay scale, and then you pick the channel that you assign to this decay scale in the proportion of respective probabilities of the decay channels. Another neat algorithm that is typically used is actually a winner-takes-all algorithm. In that case, you generate a decay scale with a probability distribution for the first decay, and another decay scale with a probability distribution for the second decay. And then you pick the channel I with the smallest decay scale to occur. Again, in a typical algorithm, it's in a typical Parton shower algorithm, the whole thing is actually inverted, and you would pick the larger scale. This allows you to use much simpler overestimates, because now you have much simpler functions to actually draw from, meaning that it's typically an easier numerical problem. Typically, you would use something like a winner-takes-all algorithm. However, there are tons of ways of actually doing this competition in a right way, kind of reordering how, if you pick a channel first, or if you pick a scale first. That can be very important in the actual speed and efficiency of the method. For example, let's say you have, for a particular type of particle, you have 1 million decay channels. Then having to sample 1 million different scales first before deciding on taking one would be quite a nightmare. So then you might do rather something that is similar to the first one. Depends really on the question that you're after, what algorithm you want to use in order to do this. Okay, now moving on. So finally, with this, we have all the technical tools to construct a Parton shower, which in the simplest approximation, the splitting functions that we looked at in the end of the last lecture, and that Dave has already and will also talk a bit more about, are fully factorized from the hard scattering cross-section. And again, in the simplest approximation, the decays of particles are independent of each other. And just like in radiative decays, the decay of an isotope over here in the sample and an isotope over here in the sample are, to first approximation, independent. The only difference here is that they are ordered in a decreasing sequence of scales in order to retain this memory, just like in the nuclear decays, you'd be ordered in a decreasing sequence of times. So overall, the splitting process can be iterated, meaning that the result after n splittings, after n decays, is actually forming the hard scattering cross-section for the next emission. Symbolically, this is often written in terms of a shower, quote-unquote, operator, F, that looks like if this shower operator acts on a phase space point with n partons, and you want to measure the observable O on that parton, on that phase space point, and the shower is allowed to produce any emission scale between a maximum value and a minimum value, the result is that potentially the sample itself does not change, so the number of particles stays the same. The probability for this to happen is the no splitting or no splitting probability or pseudo factor, and the observable that you measure is still the observable with only n finite state particles. And then you have a term where a splitting occurs at a particular scale t. Again, kind of keeping in mind that if it happened at a particular scale t, it did not happen before that scale t. And once you do that, then this can act as the seed for a subsequent decay further, that then defines a shower on these decay products, acting sort of now on an n+1 body phase space, measuring the observable O again between scales t and the minimum scale. Through the pseudo factors delta, the shower itself is an all-order calculation. We saw that this delta is an exponential of a splitting function, and the splitting functions themselves are proportional to a strong coupling constant. So expanded out, this gives you terms of all powers in the strong coupling constant. Also, funnily, both of these terms in this equation are individually finite, because these are just exponential functions, exponential of a minus an integral that diverges. So e to the minus infinity is luckily 0, which is perfectly finite. So it means that both the virtual correction approximation that the shower uses and the real emission approximation that the shower uses are individually finite. You don't have to sum them up together. You don't always have to sum them up in order to get a finite result. You can look at them individually, and they're individually finite. There is a question, so go ahead, Ross.
Hi, I was just wondering on that equation why the delta n factor is not from t min to t, if it's not the sort of no splitting probability from some minimum time up to the time that you're currently integrating.
Very good, very good. Should have said that again. So typically, yeah, the way how the shower is written down is actually from a high scale to a low scale. So at odds with how I introduced the algorithm. So in this case, then if you would think of it to generate indeed emissions between a minimum scale and you walk up in scale values, then you're absolutely right. How a shower is usually run for an event generator is the other way around. You start at a high scale and move on towards low scales. And the reason for that is that the highest scale that you're interested in is given by the largest energy transfer, momentum transfer, so the hard scattering cross-section, which you've already calculated previously. So the idea is in order to attach a shower to a hard scattering cross-section, it's better to start at a high scale and move down rather than starting at a low scale and try to move up and hit this high scale somewhere. It will be very difficult in a sense to move up and randomly move in random steps, move up in splitting scale and actually hit the right scale in order to be able to produce a very, very high energy transfer that would produce the hard interaction. So that's why you typically reorder it a bit.
Yeah, thank you. That makes sense. So should the integration limits go from sort of Tmax up to Tmin in that sense, or?
So the integration goes from exactly from Tmax to Tmin indeed. Yeah.
Okay, thank you.
Okay. So luckily, this is already said the first page here, first thing here. So indeed, the potential will develop from a higher propagator virtuality and large angles to small virtuality and small angle. So if you have a hard scattering here, this should be an ultraviolet scattering here, high energy. Then what can happen is what will happen is that these particles will branch, producing sort of a lower energy particle in the final state and maybe in the initial state, and branch. And these decays might branch further, or the initial scattering particles might branch further and further and further and further. There are several choices that will influence how this sequence is mapped. One of the key ones is actually how do you order these emissions? So I say in the first sentence that things move from high propagator virtuality and large angles to small propagator virtuality and small angle. So would you want to order these emissions in terms of propagator virtuality alone, or only angles alone, or a mixture thereof? For example, a transverse momentum. These are choices that you have to make that will, if you look at the integrals, actually not change the integral of a single emission, but will change the overall effect of having multiple emissions due to this ordering thing. So you'll hear about what choices people typically do in the shower lecture. For now, to say it's a choice, and choices are always bad. The next choice is how do you map the phase space of emissions, meaning if you have produced a state with on-shell four momenta of all particles have their right p squared equals m squared. If you now branch a single particle and produce new particles, all of these particles should again have p squared equals m squared. However, you can't branch a massless particle into two massless particles. That would violate momentum conservation. So you would have to maybe take momentum from somewhere else in the whole event in order to make this work. How do you do this? An infinite way of doing this, and some are better than others. Finally, the way how this decay was motivated was by adhering to basically statistical mechanics of when do nuclei decay, and then linking it to the pseudo-Docker factor, which is again linked to virtual corrections in a certain approximation. I never mentioned anything about quantum interferences here. How do you include those in the shower? How are those approximated? That's also a big issue. Choices are on average a bad thing. What is also clear is that the most dominant features, the thing that you will see most clearly in the detector from this branching process, will be determined by the highest energy emissions of additional particles. Higher energy particles are always easier to detect than lower energy particles. So if you want to be independent of the choices, or try to be as agnostic to the choices as possible that you have in the shower for the distribution of the very hard emissions, very high energy emissions, on very well angular separated emissions, it's best to improve the event generator, best to improve the shower beyond the approximation that we've used in order to derive the Sudakov form factor and derive the evolution equation. And this is the goal of a field called matching and merging. You'll again have a dedicated lecture to that. We're pretty fortunate for this school to have a lot of dedicated lectures on these specialized topics. But let me just give you the gist. Let us compare a next to leading order calculation, like we have written down in the end of the last lecture, to the expanded version of a Partner-Chow. So for the next to leading order calculation, we saw in order to describe an observable at next to leading order accuracy, we needed to include a tree level calculation, virtual corrections, all of these loops. We needed to include real emission corrections, and we needed to make sure that the integrals here that we do are finite for the particular observables that we're interested in, called infrared safe observables. And we did that by subtracting from these integrals from the real emission integral its singularities and adding them back in to the virtual corrections in order to make sure that we've only added a 0. For the Partner shower, now if you only think of it its expansion, the Partner shower itself will act on a tree level prior distribution and will distribute that over a larger potentially a larger set of final state particles. And if the Partner shower has not produced any emission, meaning you look at the first term in the shower equation that we just saw, which is proportional to the no emission probability, and you expand this no emission probability out, the first term in the no emission probability will just be negative the tree level matrix element multiplied by the splitting kernel. This is the first term in the expansion of this exponential factor. Similarly, the Partner shower can create real emission events, and it does so by starting again from a tree level prior distribution for n particles and producing an emission according to the approximated real emission matrix element that only contains the singular structure. So what you see is that because the Partner shower provides an approximation of real emissions and virtual corrections, these two calculations overlap. If you want to combine them, you need to remove this overlap both of the virtual corrections and of the real emission corrections. Now, that sounds annoying. Things overlap. This is a bad thing. However, this is actually a blessing in disguise. Because what you can do is you can subtract the Partner shower result, all of these things, from the next to leading order cross-section, and then use this subtracted version of the cross-section as the seed from which to, the prior distribution from which to start a Partner shower. What this gives you is a way of generating events, so phase space points, not only observables, but phase space points at next to leading order accuracy. This is going to be the next slide, and I think this is one of the kind of 2 or 3 more of these messy equation slides. So again, big advantage is that we can actually finally generate next to leading order events. So let me do that first by adding a couple of zeros to the next to leading order cross section. I'm not going to do anything except add zeros. So the next leading order cross section, right? There was a part up here, and there is the subtraction of the virtual correction down here. Now I add to that the approximation of the minus the approximation of the shower virtual corrections, and add that back down here in the green, in the pink, sorry, with a negative sign, such that this pink term and this red term here cancel each other. I've only added a 0. I add another 0 into the real emission terms. There I subtract the real emission contribution of the Partner shower, which does depend on real emission kinematics. Or I subtract the real emission, part of the Partner shower, and I add it back in this pink term here. again, only added a 0. I've not done anything to the cross-section. This is still the precise Nextstelline order cross-section. However, what I've done is we have now managed to make this these two black curly brackets separately finite. In the real emission diagram, the real emission contribution, you subtract out the real emission contributions singularities with the same observable dependence as you would need for the real emission contribution. So this is a finite integrand that you can use then in order to sample from. Similarly, you've done that for the virtual corrections, where kind of the virtual corrections themselves were sort of regularized by the subtractions. You put the real emission subtractions into that same bucket and add the shower on top of it. Again, this cancels. These things are finite. Everything's finite. The only thing that is not finite is the last pink bit, because that again depends on different observables. So it would only be finite if the observables are infrared safe. However, if I were to start the shower, initiate the shower on a tree-level prior distribution, this pink thing down here is exactly what the shower would produce. Go back one slide to see that again. If the shower acts on a tree-level distribution, it would produce minus the tree level times the integral over the splitting function as virtual correction, and as real correction, the tree-level prior distribution times the splitting function. Same here, tree-level prior distribution times splitting function with n+1 body dependence, and tree-level times splitting function times -1 for n body dependence. So if this term here, this pink term here, is removed completely from the equation, and you use all the rest, you use the black curly brackets as the prior distribution from which to start a Parton shower, then the Parton shower itself will fill in this pink distribution. So this allows then to generate events because these brackets are separately finite. And it makes sure that once you start the Parton shower fills in the remaining pieces of the quote-unquote zeros that I've added in order to reproduce the correct Nextstelline order cross-section. This is called a Nextstelline order matched calculation, and within the MC at NLO approach. So I'm checking of how am I doing with time. I have maybe 15 minutes, so not too bad. This is how you would combine the Nextstelline order calculation with the shower. There are several other ways of doing it that basically have a similar type of structure, only choose to use slightly different ways of defining the splitting functions in order to produce some good qualities that you would like to have. For example, that these curly brackets are individually themselves positive definite, which is not guaranteed necessarily here. There's going to be a whole lecture on this. So I'll leave that lecture to show you all the subtleties. There are, as usual, quite a few. And this is still an active field, even though by now, a 20-year-old field. So it's a time-honored tradition of Monte Carlo event generators to do matching. And there's going to be a whole lecture on it. However, still not there in order to describe data at the LHC at a sufficient level, typically. And that is because Nextstelline order match calculations describe virtual corrections and the additional corrections with one final state particle extra in the game at tree-level accuracy. Quite often, experimental data analysis require sort of more particles to initiate jets than just one or two extra from a simple process. For example, if you look at the transverse hardness measured in a detector, which is typically something that is very high for beyond the standard model signals and somewhat low for standard model backgrounds, these observables depend on any number of jets. So having a low transverse hardness typically means that on average you only have one hard, well-separated jet. Having sort of an intermediate transverse hardness typically means that you have 2 or 3 hard jets that are well separated in an angle to each other, and so on. Going higher and higher in transverse hardness means that you need more and more hard, well-separated jets in order to describe the distribution. And hard, well-separated jets are not what the Parton shower is good at, because the Parton shower approximation is based on this universal factorization of the matrix element, which was derived in the limit where energies and angles are small. So only there does it really make sense. Only there can you say anything big to it. So you need a calculation that describes, for example, this spectrum in a sufficient way. The shower can't do that. Next to leading order maps calculations can do that only for, say, small values of this transverse hardness. You need something else. And the trick is to instead consider stacking simple, let's say tree level or next to leading order calculations on top of each other. So having a tree level calculation for 1 jet, for 2 jets, for 3 jets, for 4 jets, and so on, and stacking them on top of each other, using, in order to make the whole thing consistent, a bit knowledge of the Parton shower. This is what defines a merging scheme, a multi-jet merging scheme. So the task of a multi-jet merging scheme is to describe events for simple final state with 0, 1, up to n well-separated jets in a combined calculation, where the rate of having n jets is determined by a fixed order calculation, and the jet structure is determined by the Parton shower. However, if you have a calculation, say with 1 additional jet, and you shower that, the shower will introduce a 2nd jet, a 3rd jet, and a 4th jet, and so on. So these calculations, if you shower them, will start overlapping again. So you need to do something about this overlap. And it's best to take inspiration from the shower there, because the shower itself already avoids overlap in its the way how it samples real emissions, right? It samples an emission at a scale t. It happens, the next emission is at a scale t2, which is slightly smaller than t, and so on. And showers themselves produce these all-order real emission corrections without any overlap, and they still make sure that the inclusive cross-section itself is preserved by correlating the no emission probability with the emission probability in order to make sure that everything is unitary. Everything, the inclusive cross-section is preserved when you are not sensitive to any of the emissions. And the way how it does that is by removing the emission rate from, so for having an emission from the rate of having no emission. So in a sense, think of it as you have a sample of 100 events with n partons only, distributed according to an n parton differential cross-section. Once you shower that, you will have a piece where you still have, say, maybe 100 events that remain n parton events. And you have 900 events that are n plus 1 parton events now, with the rate, the prior distribution rate times the integral over the emission probability, which includes this splitting kernel and the Sudakov factors. Now, if you do a second emission, then you can again split up this part where you have a first emission into a part that stays an n plus 1 body configuration, or you have a part that moves into an n plus 2 body configuration. If you're not sensitive to any of these emissions, then you can just sum up all of these things, all of these buckets again, and you recover the original bucket. You'll always keep the 1,000 events, and these 1,000 events had originally been distributed according to the differential cross-section for n particles. How you can think of it is, again, that you take your original rate and you remove your rate of the first emission in order to calculate what is the rate of the n-parton event staying intact. You could, in principle, do the same thing if you want to stack calculations on top of each other. You calculate the rate of the first emission, you calculate the rate without an emission, and you subtract the rate of the first emission from the rate without an emission in order to get the bucket here. An idealized merging method would actually do that. So this is, I promise, I think this is the sort of most messy slide that I have. It will be less messy in the following. So again, the chain of reasoning is you pre-calculate a differential cross-section at a certain accuracy that you're interested in for an n-body state, n+1 body state. Then you make this n+1 body state parton shower-like. So you include this additional no emission probability, which makes sure that this is a separately finite term, just like in the shower. And then you remove this sort of re-weighted real emission correction from the inclusive rate. So this is, again, kind of, to add something and you subtract it from the real emission rate to get the smaller bucket on the last slide. You can make this more parton shower-like by realizing that this first term here, on this first line here, is actually nothing else but the seed cross-section or the prior distribution multiplying the no emission probability between the maximum scale and the minimal scale, just like in the shower, right? This is the first piece of the shower. This is now the second piece of the shower. There is a caveat here, meaning that this is really only true if the parton shower would exactly recover the real emission contributions. So that can be true in some special cases, but not always. So this is why there's a bit of an approximation here. And once you know, this effective approximation, there's kind of this approximation to make it more shower-like. You can think of, well, how can I make this into an effective description that I can use in order to not have to calculate these complicated factors that might depend on the details of the shower from the outside myself. And the way how you can think about it is that what these no emission probabilities do is they say, if you have an event that has more than these n jets, you would want to veto it. That is then kind of removing the amount of events with more than n jets from your n jet differential distribution. So you can replace these no emission probabilities by an actual veto on the event, on your input, on your sort of input events, in order to produce this these factors to a certain approximation. And you can do that also for the reals. So there are several ways of thinking about how to combine multiple tree-level calculations or next to leading order calculations in the same way with each other and stack them on top of each other with these types of methods. And depending on which line you like best, various implementations are available. And they depend on various sort of approximations that you make in order to say you indeed want to preserve the inclusive cross-section, or maybe only up to an approximate sign and so on. Again, there's going to be a whole lecture, so I'll leave the fun to that. The main thing that I want you to take from this is, in order to preserve the inclusive cross-section, the cross-section of an n-body state without being interested in n+1, n+2, n+3 body states, saying you only look at the number of, so n is larger or equal than 5 jets rate, for example. To preserve the rate for these types of inclusive observables, what you do is effectively you add real emission corrections and you subtract them as virtual corrections in order to preserve the cross-section. Why do I keep pounding this drum? Because I want to go back to the bigger picture, probably after the break, to be honest, and explain how you would handle multi-partner interactions. So now moving from the Partnerschau to having multiple interactions between the constituents of the composite objects that we collide. And here, the assumption will again be that we want to preserve the inclusive cross-section. And if we want to preserve the inclusive cross-section, the easiest way of doing that is by subtracting what you add. So I think now is a good time to have a quick to stop, and I can take a couple of questions, and then we continue after the break. So I don't see if there's anything in the chat.
Not yet.
Not yet.
And I also don't see any hands raised, but maybe things have to settle down a bit, and everyone has to think for a minute.
Good, yeah.
Questions. Could you remind us what is an inclusive cross-section? Is a question in the chat.
Okay, good, yeah. So an inclusive cross-section is the cross-section for producing n or more particles. So let's say you're interested in the rate of having 5 or more jets. That would be an inclusive statement, because that would include both, well, having 5 jets, but also having 6 or 7 or so on. And cross-sections themselves, the cross-sections that we calculate in perturbation theory, in fixed order perturbation theory, are defined in exactly this way. So whenever you if you look into Pesky and Schroeder, and you look at how a cross-section is calculated, you will always find the ominous plus x somewhere. So we have proton-proton goes to, say, an electron-positron pair plus x, simply to indicate that the calculation that you've done at a fixed order, indeed, by the way how you've done it, by defined it, actually implicitly includes a statement of higher order corrections that you have not calculated yet. Another way maybe of thinking about this is when you factorize the cross-section into a partonic cross-section and the Parton distribution functions. The Parton distribution functions themselves depend on a factorization scale, and everything below this factorization scale is actually integrated out into the values. Everything, every emission, every virtual correction is integrated out into the value of the Parton distribution functions at that factorization scale. Now, if you would decrease the factorization scale, you might start seeing more you'd start seeing a larger rate that could be due to real emission corrections and virtual corrections. So maybe that's also a good way of thinking of what is inclusive. Things are still integrated into the PDF that you might then resolve if you do a higher order calculation. Does that help? Hyun-Bin?
Hi, so could you please remind me what is the meaning of the O by n in the n plus one dimensional phase space? So I mean the red color at the middle side.
You mean this here?
Yeah, that's right.
Perfect. Yeah. So the way how to think about this is maybe to go back to this Parton-Schauer evolution equation. And in here, we have these exponential factors that are integrals over So e to the integral over the real emission phase space, integrating as the real emission or the splitting kernel. And now if you would expand that out, the observer dependence would still be ON, but you'd have an additional integral over the splitting functions. This is how you should maybe think of these types of terms. In a practical manner, how you could think of it is you take your n+1 body phase space point and you run a jet clustering on it. And that jet clustering might produce, if you cluster two particles together, might produce an n-jet state. And now instead of evaluating your function, your observable on the n+1 jet state, you would simply you'd simply evaluate it on the clustered state. And in this particular, if you think of it in this particular sort of add subtract type of manner.
Ah, great. Perfect. Thank you.
You're right. There is, and it's kind of it's actually a very good point, because there are subtleties in how to do this thing. Quite a few. More in the lectures, I would hope.
And actually, that slide also relates nicely to the first question about what an inclusive cross-section is, right? Because all of this merging procedure is only necessary or only makes sense because we're always talking about inclusive cross-sections for the n particle process, for the n+1 particle process, and so on. So you first have to make those exclusive before you can add them together, right?
Yeah, exactly. You have to make them sort of n and only n particles in order to, so you have to, exactly. That's a good way of thinking about an inclusive cross-section. An inclusive cross-section is adding up cross-sections with n and only n particles, n+1 and only n+1 particles, and so on, into an inclusive whole.
All right, I don't see any further questions, and we're also at the coffee break time, so I think it's a fair point to make a break and let everyone get a coffee and come back in half an hour at 11:30 for the fourth and last, but not least, part of the Monte Carlo lecture.
Sounds good.
Thanks, Stefan. Thanks, everyone. See you in half an hour.
In a few minutes.